want to cover a little bit more about probability. We've got a couple more tricks up our sleeve, and you can get a little bit more experience. So, with that said, let me remind you what we did last time about probability. The definition of the probability of an event happening. We call that event E, okay? Just to use a letter. If E is an event in the sample space with the number of elements of E outcomes and the number of elements of S equally likely outcomes, then the probability of E is defined as the number of elements of set E divided by the number of elements in the sample set. So remember, we're going to do a bunch of counting. Remember that the sample space is the set of all possible outcomes with no limiting restrictions. Okay? Also remember that probabilities always come out to a number between 0 and 1 inclusive. They can be 0 and they can be 1, but somewhere between 0 and 1 you're going to get the answer. Okay? Now there are rules that are always followed in probability. That is, the probability of any event, as I just said, is a number between 0 and 1. Inclusive means it could be 0 or it could be 1 also. The sum of all the probabilities of the possible events in a sample space will be 1, because one of them has to happen, right? Kind of a deal. And the probability of nothing happening, or the empty set, is 0. Okay? But this second one's going to be the most useful. They all add up to 1.
Allow me to demonstrate.
Okay, we did this one. For instance, 3 card hands are dealt from that's a hand with 3 cards, are dealt from a 52 card deck. Okay, maybe you're playing guts or something. The number of queens in each hand is actually recorded. And we want to know, what is the sample space? What are the possible things that can happen? And what is the probability of each of those outcomes? Well, the sample space is the set of all possible outcomes with no restrictions. And we remember we dealt 3 cards and we're counting the queens. So the possible things that can happen are we can have no queens, we can have 1 queen, we can have 2 queens, or we can have 3 queens. We only have 3 cards, okay? So let's do the 4 possibilities. The probability of no queens, well, let's see. How many ways can we get no queens? Let's look at our sample space first. How many ways out of 52 cards can I get 3 cards? That's going to be a combination of 52 cards taken 3 at a time. Remember that it's a combination because order doesn't count in a card hand. Okay, now how many ways can I get no queens? Well, it's going to be a combination of 48 cards, the ones that aren't queens, taken 3 at a time. Okay, we subtracted the 4 queens basically. Okay, so that's the probability of getting no queens, and whatever number that comes out to, you could get that from your calculator. The probability of getting 1 queen, well, this is going to involve the multiplication principle. Let's do our sample space first. It's the same one. Combination of 52 cards taken 3 at a time. Now, let's produce that 1 queen. That's going to be a combination of the 4 queens taken 1 at a time. We're going to use the multiplication principle now and multiply that times how many possible ways we can get the other 3 cards. And they have to not be queens. So it'll be a combination of the 48 other cards taken 2 at a time. Okay, so that gives us our 3 cards. The 1 card that is a queen and the 2 that aren't. Very similar formula for probability of getting 2 queens. The sample space will be the same. And then we have to produce 2 queens out of how many possibles? 4. So we have a combination of 4 queens taken 2 at a time. And then we have 1 card left for our 3 card hand. So that'll be a combination of 48 cards, the other 48 non-queens, taken 1 at a time. And we're going to use the multiplication principle to count how many hands that comes out to. Lastly, the probability of getting exactly 3 queens is a combination, well, we'll do the sample space, same one, 52 cards taken 3 at a time. And then we have to produce those 3 cards that are queens from the 4 queens. So that's a combination of 4 queens taken 3 at a time. Okay?
I can do that, but I don't want to.
Now how about this one? Same thing. What is the probability of getting at least 1 queen? Now this is our review. At least 1 queen means either 0 or 1. We'd have to add that, put that into the calculator. Ouch. To that. Put that into the calculator. And then also put that into the calculator.
What a dumb thing to do. I bet you wouldn't have done anything like this if Mom and Dad were
Remember,
here.
we have a better way of doing this. Remember your basic principles of probability. They all add up to 1. So if we just subtract the probability of getting none from 1, we'll get the answer. And that's a much easier calculation. Usually, well, I shouldn't say usually, but often it is. Okay? So don't be afraid to do 1 minus the complement, if you would, of your probability to get an answer.
You have chosen wisely.
Now you listen to me. I want details, and I want them right now.
Do you remember that a histogram actually displays all of the available probabilities in a sample space? Looks something like this. If those are the 4 possible outcomes that can occur in our first example here, 0, 1, 2, or 3, we're going to do a bar chart or a histogram of those numbers. Of course, those numbers, since they're probabilities, are going to be between 0 and what number? Always between 0 and 1, or any number in between. Okay? Well, the probability of 0 queens we calculated is this calculation, and if you put it into your calculator, trust me, we get 0.782, or approximately there. The probability of getting 1 queen, we had to use the multiplication principle there, remember, is going to come out to 0.204. Probability of getting 2 queens, it's getting lower, isn't it? And the probability of getting 3 queens, hardly a chance at all, but there is a chance. Okay. Now, what do we remember about a histogram? If you take all those bars and add them up,
Hey, man, check it out, huh?
what do they come up to?
Why does this keep happening?
It's always going to happen. Okay. All the probabilities in a sample space will always sum up to 1. Very important. You can use that to your advantage. Okay. No higher than 1.
I know you are, but what am I?
Now, odds. Here's the new stuff for today. What's the difference between probability and odds? Very important for you to know. They are not the same thing. And I think maybe an uneducated person would think that they were. And I think you're going to see, hopefully I'll show you, why it's important for you to know the difference. The odds of an event occurring are defined as, you ready? If E is a subset of the sample space S, the odds of E, event E, are found by reducing a fraction that is the probability of E over the probability of E prime being the probability of E not happening. Okay? We're going to reduce that fraction or ratio to lowest terms. Odds are always written, A over B, or A to B, or A to B with a colon. Okay, the odds are 2 to 1, 3 to 4, or whatever kind of a thing. Okay? And the odds against E happening are found by reducing just the reciprocal of that, the probability of E prime over the probability of E. We always have to reduce these to lowest terms. Okay?
Excuse me?
Why would we want to even use odds? Because odds are certainly different than probability. They smell a little bit like probabilities. But why would we want to use odds? And that's what I got to get across to you. Well, I would propose to you that we, you and me, wouldn't use odds. We'd use probabilities, okay? But other people, stores, newspapers, horse tracks are going to use odds, okay? And we need to understand them so we can use them, okay?
Pay attention, boys. I'll show you how it's done.
Consider, if you would, we're going to be discussing probabilities here as well. 3 horses, okay, running a race. They all have equal ability, Larry, Moe, and Curly. Okay, so they run this race. And they're the only horses in the race. So what's the probability of Larry winning? Well, hope you appreciate 1 out of 3, right? There's only one way he can win and 3 possible things that can happen. Probability of Moe winning is the same because they're all equal ability. 1 out of 3. And the probability of Curly winning is 1 out of 3. Okay, that's simple. Those are probabilities. Okay, the number of ways something can happen over the sample space. And there's only 3 horses that can win this race, so the sample space is 3. Okay, well, the probability of Larry not winning, how many ways can Larry not win? Well, that would be for Moe and Curly to win. Would be 2 out of 3. The probability of him winning is 1 out of 3. The probability of him not winning is 2 out of 3. So,
Oh, no you don't.
think about this. The odds, different animal here, different color. The odds of Larry winning, defined as the probability of the event happening over the probability of the event not happening. So in this case, that's going to be
Yoink.
1/3 over 2/3. Now let's reduce that. Remember how to reduce that kind of a complex fraction? I'm going to multiply by the LCD, or multiply by 3. And I'll get 1 to 2, or 1 over 2. The odds are 1 to 2. Okay, so the probability of Larry winning is 1 out of 3. But the odds of Larry winning is 1 to 2. Which sounds better? If you were trying to advertise for Larry, of course you would use odds, even though...
Can't you see the difference between earning something honestly and getting it by fraud?
Well, I think we smell fraud here a little bit, but that's the idea. That's what odds are. They make things look better than they are. Let's get a little more complicated problem here. Here we have a farmer that's going to pick some apples, and he's going to, of course, advertise about his apples, okay? And, of course, he wants to make his apples look better in his advertising. So let's take a look at this. He picked a sample of 30 total apples. 20 had no worms. 6 apples, somehow he counted, had 1 worm. And 4 of the apples had 2 worms. And I want you to get a little experiment with odds here. I want to find, based on that information, the odds of an apple from this sample containing no worms. Okay, what are the odds that it contains no worms? Well, that's going to be a kind of a ratio of probabilities. It's the probability of it happening over the probability of it not happening. The probability of having no worms over the probability of having some worms. Okay? The probability of having no worms is 20 out of 30, because that's the way you can have 20 out of no worms, 20 out of 30. And the probability of having some worms is either 1 or 2, is 10 over 30. Okay? So the odds of your apples containing no worms, well, of course we have to reduce this by multiplying by the LCD 30. I get 20 to 10. We still got to reduce a little bit further. You've got a 2 to 1 chance of having no worms. That sounds real good here. Makes you want to buy apples here, maybe. 2 to 1, not very good, actually. Okay, it's really 2 out of 3 if you talk about probabilities. But 2 to 1 sounds real good. What is the odds of having at least 1 worm? Well, once again, it's going to be the probability of that event happening, the probability of having at least 1 worm, over the probability of not having at least 1 worm. Well, the probability of having at least 1 worm means you're going to have either 1 or 2 worms. There's 10 apples that have that, so 10 out of the 30 is your probability of having at least 1 worm. Probability of not having at least 1 worm means that you have none. 20 of the apples have no worm, so that's going to be 20 out of 30. So the odds defined by the probability of the event happening over the probability of the event not happening is going to come out to 10 to 20, or reducing 1 to 2. So you have a 1 to 2 odds of having at least one worm. Oh, that's a very poor advertising. I'm not buying that. How about the odds against, now against changes everything, against an apple containing 2 worms? Against means we're going to flip it. We're going to do the probability of the event not happening over the probability of the event happening. So we've already taken care of the against because we flipped it. Okay? So the probability of not having 2 worms, that means we have either 0 or 1 worm. That can happen 20 plus 6 ways. Right? We had 20 with no worms and 6 had 1 worm. The other 4, of course, had 2 worms. So the probability of not having 2 worms is 26 out of 30. The probability of having 2 worms is 4 out of 30. Now we're doing it against, so we put the complement on top. And to reduce this, we get 26 over 4, or a 13 to 2 odds against an apple having 2 worms. Okay?
You'll come again.
Now let's look at this one. I notice every time I get a Slurpee cup, I've got the odds, or I get a cereal box or something. They always use odds, don't they? Let's take a look at this. If the odds of winning a free iTunes song when you buy your Slurpee are 1 to 7, let's see if we can work backwards. What is the probability of winning? Because probability makes a little more sense to me. I know the odds are 1 to 7. Not 1 in 7, 1 to 7. What is the probability of winning? Well, the odds is a ratio. It's not a count. It's a ratio between 2 probabilities. And we know that it comes out to 1 to 7. Okay, that's the odds.
Are you pondering what I'm pondering?
Now, odds is a ratio of probabilities. Probabilities is a ratio of numbers. Okay, so we have to get the numbers to figure out probability. The number of ways that the event can happen is one way. What's the number of ways in the sample space in this example? Think about it. The number of ways in the sample space is the event happening plus the event not happening. And this would be true in any problem, okay, not just Slurpee problems, okay? So basically you're going to add the top and the bottom all the time to get the sample space. And the number of ways the event can happen, at least in this case, is just 1. So, with that said, while the odds are 1 to 7,
There's something wrong with us. Something very, very wrong.
I don't know how honest it is, but the probability is 1 out of 8. And you can hope you appreciate, as that number gets quite large, maybe instead of 1 to 7, maybe it was 1 to who knows what, or 2 to 1,000,000 or something like that. They can really kind of change the way things look and make things look better or worse. Of course, they always make it look better. Okay?
I'm back, baby!
A whole nother principle I want you to look at. You remember this, hopefully. The Inclusion-Exclusion Principle was like on our first test when we studied sets. And what it involved was finding how many members were in a union. And what we did was we added the number in one set to the number in another set and subtracted the intersection, because that got counted twice. Well, then, remember we basically used the same thing. We just called it something different. We called it Morgan's Law when we started using Venn diagrams, because a union really meant or, and it really was the same thing. And we added the number of members in each set, and we could get the union, and subtracted out the intersection, because the intersection was counted twice. Well, now we're going to use it yet again in talking about probability. So this is a very useful concept. No matter what you call it, doesn't really matter what you call it. Maybe you want to call it Witty's Law. Okay, but anyway, the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B happening at the same time, or the intersection of A and B. Once again, the probability of A or B happening is that's the probability of that. Okay, and that's hard to find and hard to count. Is going to be the probability of A. Note that the intersection is in there. Plus the probability of B. Note that the intersection is there and again. Minus the intersection. We have to take it out because we counted it twice. And that gives us the probability of A or B.
Allow me to demonstrate.
Okay, well, let's try using this. Here's a problem. If I give you the probability of A union B is 0.8, and the probability of A is 0.4, and the probability of B is 0.7, I want you to find the probability of A intersection B. Remember what A intersection B is, this area in here. Okay? Now, why would we want to find that anyway? Do you remember that whenever we started filling things in counting or in Venn diagrams or any problem, we always wanted to start with the middle. And once we had the middle, we could work our way and figure out all kinds of things. Okay? So that's why we'd want that. In this problem, let's fill things in. Okay, we know the probability of A union B is 0.8. We know the probability for A is 0.4. We put that underneath. We know the probability for B is 0.7. We put that underneath. But we don't know the probability of A intersection B. So that's kind of our variable. Let me add the 0.4 and the 0.7. And 0.8 equals 1.1 minus what? Think about it. It's 0.3. It's got to be 0.3. Okay, you could solve the equation too if you wanted to do it that way, but that's the idea. And we could find that using this, and that's about the only way to find it. Okay?
I have a feeling some bad stuff is about to go
Well, now that we know that, somebody might ask you, what is the probability of A not happening and B not happening? You understand what that means? A prime intersected with B. Remember, an intersection is an and. What is the probability of A not happening? Where would that be if this was a Venn diagram? A prime. Okay? And at the same time, intersect that yellow area with B not happening. Now, where do they intersect? Well, what part is in both? It's going to be this area. Okay? And if you needed to count that, given all the other numbers, where would we start? Well, it would be awful nice to know that 0.3. Okay? And then we know the 0.3, and we know all of A is 0.4. All of A is 0.4. So this area in here, remember we did that with Venn diagrams, must be 0.1. Okay, now let's fill in some more. We know the intersection is 0.3. See why we wanted that intersection? And we know all of B is 0.7. Since we know all of B is 0.7, and the intersection part is 0.3, this part must be the 0.7 minus the 0.3, or 0.4. Okay? Now remember what we're trying to find here, that part on the outside. Don't forget that the whole sample space is 1. So if we subtract those three numbers, 0.1, 0.3, and 0.4, from the magic number 1, we know that it's 0.2. So we can find out really anything using this principle, this addition formula for probabilities, and the idea that all the probabilities in a sample space add up to 1. Very important. Don't ever forget that one.
Thank you, sir. May I have another?
Okay. Well, let's see. Let's try and find, given all these numbers, I'm going to save the numbers from last time, the probability of A prime unioned with B prime. Now wait a minute, let's get a picture of this. A prime, everything but A, unioned with everything but B. You know, if we union those two, that means just put them together. That means we have everything but that intersection, don't we? Everything but that intersection, you can add up the 0.1, the 0.4, and the 0.2, or subtract it from 1. And you get 0.7. So we can do all kinds of crazy manipulations. And why would you want to do that? Well, people probably aren't going to ask you about A and B, whatever. They're going to ask about what is the probability that this won't happen? Or what is the probability that this won't happen and this will happen? Or kind of a thing. And you'll have to put it in union and intersection language. But once we have it, we can use these principles to solve that. Okay? For instance, look at a problem here where we have 4 boys and 2 girls randomly seated in a row. Okay? We have to seat them. Let's look at our sample space. How many people can sit in the first seat? How many people can sit in the second seat? How many people can sit in the third seat? And on down. It's basically going to be 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. Which comes out to the number of ways we can seat these kids is 720. Trust me. Okay? Now that's not the question. Okay? I think you already knew that. I want to know, what is the probability...
No, I can't take it. I can't take it, Jerry.
That's a tough one. We can do it. What is the probability that a boy is seated at the left end or a girl is seated at the right end? I don't even know where to start. But from now on, I hope you'll know where to start. Whenever you see an or, you smell union. Okay? So we're going to use... We're going to try and figure out all of these and use the probability addition principle. Okay? Let's figure out for A, basically. A boy is seated at the left end. That's the first event. What is the probability that a boy is seated at the left end? Well, let's see. How many ways can that happen? We got a choice of for the first thing, we got a choice of 4 boys. Okay, and then after that you can seat anybody however you want. 5 times 4 times 3 times 2 times 1. Okay, so that's what I would call A, and that number comes out to 480 over the sample space 720. So 480 over 720. Okay, now that's the probability of A. Let's look at the probability of B. A girl is seated at the right end. Well, let's see how many ways that can happen. We have 2 girls. So I put the 2 girls, one of the 2 girls in there, and then after that, once again, I can seat anybody I want. 5 times 4 times 3 times 2 times 1. Okay? So, if you multiply all that out, I get 240. So there's 240 ways that I can do that out of 720. Okay, you can calculate that if you want to, but I'm just doing theory here. So we have A, we have B. We're looking for A union B. We're going to need A intersection B, which really, if you understand, is a boy seated at the left end and a girl seated at the right end. Well, let's count that. That's going to have one of 4 boys. I put the 4 on the left, and one of 2 girls. I put the 2 on the right. And who do I have left after that but the other 4 people that I can put in any order? 4 times 3 times 2 times 1 in the middle. And that number, I promise, comes out to 192 out of 720. Okay? So, if we want to do the OR, remember an OR is like a union, we're going to do A plus B minus the intersection of A and B. Well, we figured out all those things. Individually, they were easy. Okay, take a little bit at a time. So basically, let's take our time here, and a boy seated at the left end or a girl seated at the right end is going to be A plus B minus the intersection over 720. And that's when you're going to use this. Anytime.
With all due respect, sir, I believe this is going to be our finest hour.
It's going to be tough, but anytime you have an OR is when you're going to use this addition principle of probabilities. A plus B minus the intersection of A and B is going to equal your union.
That's the fact, Jack.
Okay?
Hey, that's just crazy enough to work.
Let's talk about this when the 2 events are, quote, mutually exclusive. Maybe we don't know. Let's talk about what the heck mutually exclusive even means. Okay? Consider this problem. I want to know, what is the probability that 2 dice roll a 12, or when you roll the 2 dice, the first dice is a 5? Two events. One is that you roll a total of 12. The other is the first dice rolls a 5. Well, let me warn you, this one's going to be a little bit weird. Okay? It is an OR, so we are going to use the addition principle. So there it is, the addition formula for probabilities. So we need the probability of A, the probability of B, and the probability of the intersection to figure out the OR, or the union, don't we? Well, let's see. The probability of A, how many ways can that happen? How many ways can I roll a 12? Only one way. Okay? One out of what? What is my sample space? Well, I'm rolling 2 dice. So my sample space is 6 times 6, right? So my sample space is 36. So the probability of rolling a 12, probably already knew, is 1 out of 36. Now what's the probability of the first dice being a 5? Well, there's 6 ways I've pictured here that can happen. There's 5 and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, and 5 and 6. Okay? So there's 6 ways over the sample space, which we already know is 36. I'm going to leave it just like that, just for a second. Okay? Now, I want to subtract out the ways that it can intersect. In other words, the probability of rolling a 12 and at the same time the first dice being a 5.
That, sir, is illogical.
Well, it can't happen, can it? So that comes out 0 ways can that happen. So the answer for the OR is 736. Okay, that one was a little easier because the intersection came out to 0. Well, anytime the intersection comes out to 0, we call these events mutually exclusive, which is going to change our addition formula. We'll have an addition formula for mutually exclusive events. So if 2 events are mutually exclusive, we say they're disjoint, or they can't actually happen at the same time. They can't happen at the same time.
Well, duh.
Then, in other words, their intersection is 0. Well, then we have to change the addition formula and not subtract 0, and it's just
I know that, dude.
the OR is the probability of A plus the probability of B. All you have to do is add them. If they're mutually exclusive, all you have to do is add them. You can go ahead and subtract the 0 if you want. It won't change. But when you see this, I don't want you to be surprised that, hey, wait a minute, they changed that formula on me. Well, they didn't. It's just that in that one instance, the events are mutually exclusive. They have no intersection. Now there's the other theorem, which you probably already know very well also, is the complement theorem. As I said, we already know if this is set A, the probability of A, if we knew it, the probability of event happening is 1 minus the probability of event not happening, isn't it? Because the whole sample space has to add up to 1 as far as probabilities go.
Pay attention to me, boy. I'm not just talking to hear my head roll.
I think you already knew that, but it's going to come into play a little bit differently when we talk about mutually exclusive events. Let's look at one more example. In this example, 5 cards are dealt from a standard 52 card deck. Okay, and we're playing poker here kind of a thing. The probability that at least 1 card is a spade of those 5. Well, one way to do it is to find out what's the probability of 1 spade, what's the probability of 2 spades, what's the probability of 3 spades, add that to probability of 4 spades, add that to... It's going to be quite a lot of work. If we do it the hard way, the probability of 1 spade, exactly 1, is going to be, let's produce that 1 spade. It's a combination of 13 spades taken one at a time, times the other 4 cards that are not spades. So that'll be a combination of the other 39 cards. That's 52 minus 13. That's where the 39 came from, taken 4 at a time, over the sample space, which is our 52 cards taken 5 at a time. Okay, that's just the probability of 1. We add in the probability of 2, exactly 2. Let's see. We're going to have, to produce those, 2 spades from the 13 times the other 3 from the 39, which is 52 minus 13, over the sample space. Okay, this is a lot of work.
No, you're doing it all wrong.
Okay, I really don't think we want to do it this way. Okay, whenever you have at least or at most or kind of a thing, always use the complement principle. Let's do 1 minus the idea of it not happening. If we're going to have at least 1 card being a spade, let's have 1 minus the probability of having no spades. So then all we have to do is figure out what's the probability of no spades in that 5 cards. Well, let's see.
But that's so easy. I should have thought of it for you.
It's much easier. Note that the sample space is the same, and we're in the numerator taking in a combination of the 39 non-spade cards taken 5 at a time. Please, I say this over and over again, don't forget, you're going to use this complement theorem, this subtract the probability of something not happening from 1 way more often, typically in real life. Okay? There it is. And it goes faster too, doesn't it?
Thank you, sir. May I have another?
We do this same thing, 5 cards dealt from a standard 52 card deck, one last time with an or. I want to know if all the cards are hearts or all the cards are spades.
A clue.
Wait a minute, they're mutually exclusive. Remember what the idea of doing, usually you'd say, well, I see an or, so I'm going to use that addition principle. But since these two things can't happen at the same time, you can't have a card hand that's all hearts and at the same time all spades, unless you have trick cards or something. They're mutually exclusive. All you really have to do, and this is worthy of remembering, is add the 2 probabilities. Right? We don't need to subtract that 0 intersection kind of a thing. Okay, so let's see. The probability of getting all hearts is 13, the 13 hearts taken 5 at a time, over the sample space of 5 cards taken from the total 52. Okay, kind of a thing. That's the probability of getting all hearts. And the probability of getting all spades is very similar, isn't it? It's the 13 spades taken 5 at a time over the 52 cards taken 5 at a time. If you recognize that spades and hearts are equally likely, you could have just multiplied by 2, I guess. But this certainly is the easiest, probably the only way to do this when they're mutually exclusive. And hopefully you understand now what I mean by mutually exclusive. They can't happen at the same time.
What's all this jabber-wopping when there's work to be done?
Okay, well, it's homework time. They have plenty of examples for you to do. Let's dig in.